All right, guys. Let me try a different approach than you said. The problem with the U thing is you have to identify what U is correctly. And then you have to work with it the right way. It kind of like adds another layer of something you have to learn, right? But it is nice because later we are going to be doing a lot of stuff related to U Sept stuff. But right now it doesn't, it's just like another layer. So what's the inside function on 1a? Pi x. You circle that bad boy. So y prime, what's the derivative of cosecant of something? Negative cosecant of that thing, cotangent of that thing. Now, so that's the derivative of the outside function, right? And now I got to remember to take the times the derivative of the inside function. Yeah, so this guy's derivative would be pi. Bring him out front. So there's the derivative of the cosecant. There's the derivative of the inside piece. Okay, what about part B here? What's the inside piece? This is the inside. What's the derivative of e to something? E to something. This is here to remind me that I have to take the derivative of that inside thing also, on its own, next. So what's the derivative of this? 6x, and I just pull that out front. Y prime equals 6x. E to the 3x squared minus 4. So really a big part is identifying what the inside function is right now, doing the outside function derivative, and then doing the inside function derivative separate. Just a factor on the next step. Then if there's more chain rule, you worry about it then. You don't have to know ahead of time. Let me do C over here. So what's a way to rewrite C? I like it. Just to be double sure, I'll be like that. So it's tangent of this thing. So obviously the inside function is, yeah, this. So what's the derivative of tangent of something? Of that thing times the derivative of the inside. Let me stop for a second. So this doesn't even come into play at first. You don't give a shit that this is complicated. It's tangent of something. That guy's derivative is secant squared of that thing. Then that thing gets its own term. That's when you worry about what that is. What's the derivative of this? Yeah, so 1/2 comes down. Let me catch up to you there. 3/2. And then the inside gets a turn. Yeah. So the derivative of the inside is 3. Is that cool? I don't have to rewrite the whole thing. I really want you to understand the biggest mistake people make is to go, when do I stop doing these chain things? The minute you catch yourself thinking that, saying that, whatever, you stop what you're doing and you get some help because you're not looking at it right. You don't have to know ahead of time how many chain pieces there will be. You do them as they come.
Can you put the 3 on the secant?
Yeah, now I could put like this whole 3 halves out here. I like it. So you normally collect all your coefficient stuff out there in the front. And then this guy, if I wanted to, go down here. You can rewrite them as radicals up here. Just the thing to remember is, don't kill those, of course. One of them is inside of the secant squared. He's protected.
Yes. So this
secant squared, is that different than secant squared?
Oh, okay. All right. So let's take a second with this. So there's notation that we came up with. We kind of, math people were like, I don't want to write that all the time. Because we are remarkably lazy people. So we said, isn't there a better way to represent this without these stupid parentheses? Why don't we just put that there? Right? So these are the same thing. This, what's this? That has a what inside of a what? That has a x squared inside of a secant. So that is totally unrelated to these. These two are the same. This is its own thing. For both of these, what's inside? X, right? It's inside of a secant squared. Maybe. Yes?
Why is it over 3 times 1?
Because it was to a negative 1/2 power. So I just took that down. To be honest, I could put the 2 down there just to make it even nicer. Yeah. 3 over 2, 3 over 2. Okay. So, if you give me something, there's a 5 over here, and there's a 7x over there, just make it freaking 35x. I mean, at least do that simplification. All right, let's see, what's the last thing here? Part D there. That one looks fun. So I don't have to know anything beyond, that's a sign with stuff in it. That's all I got to know at first. I really want you to understand, you do not have to worry about what you're going to do eventually. You worry about that when it's that guy's time. It's your time. So what's the derivative sine of something? Cosine of that thing. What was the inside function? This guy. So he gets his own turn. So that's writing the rule. Writing the rule will save you from yourself. That's why I keep doing it every time. You remember the rule, plus you do the correct derivatives at the correct time in the right place. If you're trying to do everything at once, you're going to put shit together and go too far, and oh my god. So this is y prime equals cosine of tangent x. That's gross, but he's done. Times, what's the derivative of this? Negative sine of that. Right? And then the inside gets a turn. So I don't know how many chains there's going to be until I hit them each. Is there going to be another chain? Will there be another chain after this? No. What's inside tangent? Freaking x. And real quick, I forgot to say this earlier. I do always use the chain rule. Always. Derivative tangent is secant squared x. What's the derivative of x? 1. So see, that's just 1 times that. We always use chain rule. It's just when does it show up? Is when it's something other than a slope of 1. So I always use chain rule. It's just that it doesn't really show up unless the inside's worse than x, right? So in the last step here. Oh boy. Let me put that negative out here so it doesn't get lost. Times sine of tangent. And of course the derivative of tangent we said earlier is secant square. That's it. You can rearrange them if you want to, like the shell game, but where's the x? No. So here's the sine's derivative, bam. Then the inside got a turn. Here's the cosine's derivative, bam. And then the inside got a turn. That's, I just keep repeating it until I'm like, no more insides, please. What happened? Sorry? Okay. do that. All right, let's do one together because it's kind of gross. Actually, yeah, that's fine. That's fine. So if I want to take this guy's derivative, there's nothing wrong with noticing there's going to be a quotient rule, but you don't give a shit at first about that. It's my very first thing I'm worried about. The outside. And the outside is u. And that's an easy derivative. Yeah, 3 times stuff. Now this is to the second power times derivative of the inside. So again, even if you notice something's going to happen, you don't have to worry about it until you're doing that actual derivative. I'm not doing the derivative of the inside first. I'm doing the outside first. I don't have to worry about that yet. Now I worry about it. I don't know, it's just this idea of, you guys seem to think you're supposed to be able to worry about everything and know ahead of time how many things. No, my God, no. It's hard enough already. Don't do that shit to yourself. So this piece is done. It's just sitting around. You guys do this piece. I love you guys. You know, I thought you were going to do it. I'm just watching you. I'm going to catch up to you guys. So derivative of the top times the bottom minus the top times the derivative of the bottom. All over that. So we get, let's see, 3, 2x squared minus x over x cubed plus 1 squared times, crap. Let's see, 4x to the 4th minus x cubed plus 4x minus 1 minus 6x to the 4th plus 3x cubed all over x cubed plus 1 square. So then I get 3 times, let me see if you guys are cool with this. 3 times 2x squared minus x squared over x cubed plus 1 4th times. Let's see, negative 2x to the 4th plus 2x cubed plus 4x minus 1. Phew. Is that cool? I just brought those two to be with those two and made 4. Okay. There's really nothing more you can do there. I wanted to show you this real quick. What I meant earlier by I used to never use the quotient rule. So if I had like, let's make a nice little program. Like x minus 1 over x squared plus 2. And I had to take that guy's derivative. Because my teacher taught us this stupid little song, low-d, high, blah, blah, blah. Right. If you like that song, good for you to use it. The problem for me is it rhymed a couple different ways. So it's sort of like, okay, top first makes a lot more sense to me. So what I used to do is I used to do this. Because then I can use product rule and chain rule. So if I do this, I get derivative of this is 1 times this plus this times the derivative of this. Now real quick, remember how I told you when you're doing the derivative of the bottom piece, that's why that piece is minus, because there's a negative 1 on that piece, because it's on the bottom. Well, here it's happening. So I get, let's write this as 1 over x squared plus 2 plus x minus 1 times, what happens in here? Negative 1 comes down. This is now to what power? Negative 2 times the derivative of the inside, 2x. Let me make this up. Oh shit. So now I get 1 over x squared plus 2 minus x minus 1 over, oops, times the 2x over x squared plus 2 squared. So that goes down. Negative 2x comes out here. And that x minus 1 is still there on the top. And then if I needed to combine them, I would just multiply this by 1 more of those. But now you can see where things are coming from in the quotient rule. Why is it squared on the bottom? Because that is a negative 1. It's going to become a negative 2. You see that now. Why is the bottom of that squared? That's why. Why is the middle term minus? Because of this stupid thing? That's why. Right? So once you learn chain rule, you can go back and make more sense out of earlier things. And of course, earlier homework becomes really easy, but you can't do that. Too bad. Okay, maybe. All right, a little preview, and then I'll let you guys out. The funny thing to me is the next section is the same stuff we've been doing. So let me just show you an example of what I mean. Let's see, how would you do this? This guy's derivative. Building up to the idea. This is just exactly what we're just doing, right? This would be 11 times to the 10th times 4. And then you can bring the 4 there. I don't care about that. What if it would have been, what you got, Jeff? What if it would have been sine x? Let me just write it like this. Just what if it would have been this? What would y prime be? Sine x 10 times cosine. And what's cosine x? It's the derivative of sine, right? So what if I have some undefined function of x, just y? Let me put it in there. I'm not going to tell you what it is. It could be 4x minus 1. It could be sine x. It could be cosecant x. It could be whatever the shit I want, right? E to the x. I don't care. How do I do this guy's derivative? It's really just capturing what we keep doing. How do I do it? 11 y to the 10th times y prime. I love it. Y prime. Or 11 y to the 10th dy dx, because it's another way to say y prime. Right? So this is what's called implicit differentiation. Because I don't tell you what the function is. It's implied it's a function of x. Therefore, you have to use chain rules. So for example, here's my favorite example, and then I'll let you guys out of here. Yeah. Do I want to do that one? Sure, why not? Somebody tell me what that's the equation of. Of radius 4, 11. Centered at the origin. All right, let's take its derivative. What's the derivative of x squared? What's the derivative of y squared? Y is understood to be a function of x. I just don't know what it is.
2y
2y
times dy over dx.
times dy dx. What's the derivative of 16?
0.
You better do the same thing to both sides, a rule you've known forever, right? So if I do the derivative on one side, you better do the derivative on the other side to keep the balance. This feels very different, though. Yes, ma'am?
Why do you do the times dy over dx? There's no like inside. What is the inside?
There is an inside. That's an inside. Now, for this specific example, what is y? It's a function of x. In fact, I could solve for what it is. It's going to be a piecewise function, y. What happens if you try to solve this for y? Subtract x squared, and then take a square root, so you better put a, so you get the top and bottom half of the circle, right? You're going to graph this, graph the calculator, you got to do the plus or minus shit, but in y1, y2, so it makes the thing, it doesn't really meet, looks like a football. Hopefully you've gone through what I just said. It's like when Tom Brady's deflated for this. Cheaters. Over here, just to solve for the slope, I'll get negative 2x over 2y, which is negative x over y. Is that cool? Which is, I really want you... Now, in this specific example, I can solve for y. Can I always solve something for y? No, right? I could very easily mix the stuff up so it's impossible, not just hard, impossible to solve for y, right? But I can always do this idea. Now look at this. This is so beautiful. Give me a point on the circle. I can figure out the tangent line slope at that point. Because look, the derivative depends on the x and y coordinate. So I'm not just going to plug an x in. I'm going to plug the whole damn point in. Right? So what? Give me a point on this line, on this circle. What? So what about 4, 0? There's an easy one, right? So if I plug in 4 and 0, what's true about the slope there? So negative 4 over 0 is undefined, also known as infinite. And if you look at a circle and you look at 4, 0, isn't the tangent line right there going to be straight up and down? Okay, yes?
I got confused at the negative x over y. How'd you get that?
Subtract 2x, divide by 2y.
Oh,
Solve for the slope. Because now I've got a formula. Given any point, I can find the slope of the tangent line at that point. So, last thing. Here's an example of a relation that I cannot solve for y. Shit. Now this is disgusting as all shit, but you could take each thing, you could take its derivative. Every time you take a derivative with a y in it, you better put dy dx. That's the chain rule piece. Then you solve for dy dx. You can always solve for dy dx. Get all your dy dx stuff on one side, factor dy dx out. So that's going to be this next section. It's called implicit differentiation. And what it does is it allows us to differentiate things that aren't even functions. This is not a function. You can't solve for y. It's going to kind of go back on itself. Just like a circle. Does it pass the horizontal line test? Does it pass the vertical line test? It doesn't pass any damn test. So it's not a function. It doesn't pass the vertical line test. This thing is going to do all kinds of freaky little squirrely things. It's going to look like a spirograph kind of thing. And there is a way to graph this, by the way. But there's no way to solve for y. But I can use implicit differentiation to get the slope. Even if it does shit like this, here's what the thing might look like. It could look like this very easily. That could be the graph of this. I don't know. And I want to know the slope at this point. All right, I do the implicit differentiation, I get dy dx, and I can figure out the slope at that point. This thing should have a slope at every point. Of course it does. It's just not as straightforward as an explicit function. That's what we've been doing so far. This is an implicit function. You guys look like you want to murder me, but I'll be all right. We'll see if I will. All right. Okay, so that's going to be next time. I'll let us out of here a little early. Yes? Yeah, there's a few different ways you can do this. Now this, if you define y to be t, you try to figure out what x is. But there are graphical software or on the web where you can just put this whole thing in it. It'll graph it. Yeah. So do I.